Many thanks, Emma, for the introduction, and also thank you and thank Anas for the kind invitation. I'm happy to be here to present our work on the use of sub-terahertz bands for non-terrestrial networks. I this will be my first time presenting our work and this work collectively, and it gave me um, an opportunity to zoom out and see the evolution. And probably I will end up with more questions than answers, but I try to explain everything through the in a chronological order. So my name is Güneş. I'm a professor at the Department of Electrical Engineering of Polytechnique Montréal, and this work that I will present is. Of course, joint work with my collaborators, but I would like to acknowledge the contributions of Eray Güven, who will become a doctor soon, hopefully in a month or so, and then also Dr. Halit Umadi and Dr. Kürşat Tekbayık. And I will present some of their works, and of course, there are other collaborators that are cited. So before I go into the technical part, I would like to start with an introduction of my university. We are located on the mountain of Montreal, and this is the we have three buildings. This is the building that hosts electrical engineering. The green floor is electrical engineering. About 10,000 students. This is an engineering school with 7 departments, and very diverse with in terms of gender, in terms of nationality, and we are a very research intensive university. One other aspect that I would like to mention about among these 7 departments, there is quite a initiative to collaborate. So we have our research unit, ASTROLITH, which is the Transdisciplinary Research Unit for Space Resources and Infrastructure Engineering, that hosts members from all these 7 departments. Myself, I am within the Department of Electrical Engineering, and most of the research experiments today, I will talk about Polygram. So Polygram is our research lab, Groupe de Recherche Avancée en Micro-ondes et Électronique Spatiale. It's been started by Professor Bogazici in 1992. We are, I'll say, one of the largest research centers in Canada, mostly with system level expansion. Currently composed of 12 professors. Since last year, I'm appointed as the director of Polygram. We have shared infrastructure through this reservation system, and our focus is from the design of the, for example, RF circuits up until testing and measurement. The focus is on higher frequencies, millimeter wave, sub-terahertz bands, and we can go up to 1 terahertz. And there are photonic extensions. So I'll come back to the facilities later. My particular research focus is on space communications, trying to look into how we can harmoniously use terrestrial and non-terrestrial networks. So the orbital network and terrestrial convergence is one of the topics that we are looking into. When we are talking about satellites, they are actually robots, flying robots in a way. So their autonomous configuration is critical for us. Multifunctionality is critical. I will briefly talk about some functionalities like integration of communication and radar. Of course, the use of spectrum is critical. And we also try to aim hardware in the loop tests whenever we can. So our terahertz work is mostly experimental that I will explain today. We are supported by national organizations like programs of Canada Research Chair, NSERC, our research organization, MyTex, and also we have collaborations with NRC. From the industrial side, we collaborate with MDA Space on the satellite design, TerStar solution on the network design, and Volta on multifunctionality, especially through power beaming on lunar systems. So this is a quick introduction. So if you want to come visit when you are in Montreal, let me know, and I can give you a tour of the facilities. So this today's talk is on terahertz use of sub-terahertz bands, and I try to collect the what I've done over the years, mostly starting with 2019, and I will try to present this in a chronological order, mostly questioning the validity of the models that we are using. So this is how I structured the outline. I'll first explain about non-terrestrial networks and the potential role of terahertz and sub-terahertz bands. Then I will talk about two different test beds. The first one is the test bed that I started working in 2019-ish timeframe. So I'm a professor at Polytechnique Montréal for about a bit over 4 years now. Before that, I was a professor at Istanbul Technical University. So I'll start with our work back in Turkey and then expand to what we are doing in Polygram. I'll discuss the gamma mixture channel model, which seems to be a sufficiently flexible model from a statistical sense. Then I will delve into use cases, mostly on communication, but extension to multifunctionality. Later on the fifth point, I will expand it to different modeling problems. First of all, alignment, physical alignment between the transmitter and receiver. Then the extension of the system to wideband, and the two combined introduces the problem of beam squint. Here I try to add mobility, but then I noticed that there is not much in terms of the mobility that I can present, but it's also how I will finish this talk with the future plans that we want to do. And there are a lot of open issues, both in the experimental side and also on the modeling side. So to start with, the 6G vision is coming, obviously, and it is not, let's say, we don't have a solely terrestrial network anymore. Currently, what we have is on the left side of this picture, we have a well-designed, I'll say, well-engineered, let me put it this way, terrestrial network. And on top of it, we have this standalone space network that we can actually connect over in remote areas, but also in urban areas through specialized terminals. Where we are going to is on the picture on the right side, is the fully integrated network with the space component and the terrestrial component, and potentially an aerial component or near space component that is connecting the two layers. So I'm always thinking of the analogy of an Oreo cookie. So we have the two cookies that needs to be somehow, that needs to somehow stick together through a cream filling. So this is where we are going at. The non-terrestrial part is basically what is happening in the, including perhaps the drones and UAVs up until the satellites. And satellites, the most commonly discussed ones are the low Earth orbit satellites. So they are basically the satellites that have altitudes from say 450 kilometers up until 1500 kilometers. So we are expecting a big change. The main change in the space-air network is the possibility of connecting to this air network or space network through our regular phones. So we without using specialized equipment. So this is basically what is happening regardless of the frequency band, and combining all of this with the dense usage in terrestrial networks, we can see that there is um, need to increase the carrier frequencies beyond the millimeter wave um, band to actually make use of large bandwidths that can potentially provide very high data rate, and this can also help us control the interference because of the congestion that is coming up, especially with this direct to device connectivity. So how can we position this higher frequency bands? Terahertz is, of course, it is well known that as we keep increasing the carrier frequency, path loss increases. So it seems a bit disadvantageous to use these high frequencies because of the high path loss. However, they have their own unique properties, and that they can serve it for different needs of different scales, from body area networks up until interplanetary communication. So we can easily think of terahertz bands to connect two satellites. Current technology that we are using is we are basically using free space optical communication to connect one satellite to another satellite, which are called optical inter-satellite links. But they can be switched to higher frequencies. So this basically makes the hidden potential there. The very small antenna sizes actually make terahertz very appealing to create pencil beams or like even ray beams, and of course then these highly directional beams need to be well controlled, because they will be positioned on mobile platforms, and we should be able to dynamically adjust the beam pattern and potentially illuminate multiple spots. So what is happening in this from the experimental side? We need basically accurate channel models. Why do we need accurate channel models? We have well-established channel models. That's basically I'll try to give some examples to convince that we need new channel models, not only from the statistical sense, but also from the in line with the architecture of the transmitter and the receiver. First, how can we integrate these high carrier frequencies? When I talk about sub-terahertz, I mean from 100 gigahertz to 300 gigahertz band. These can serve as good connectors between perhaps between the ground station and the satellite, and also an aerial platform, air to air or air to space, and also space to space platforms can actually be a good usage scenario for these high carrier frequencies. So using sub-terahertz bands 100 to 300 gigahertz in a congested environment, terrestrial environment, needs to be better justified. So the most of the communication scenarios that we are imagining are space to space, and that is mostly because of the atmospheric attenuation. On the left side, this is basically a plot of International Telecommunication Union's channel models. targeting the sub-terahertz band. On the left side, we can see some example locations from space to ground perspective. Depending on the humidity, temperature, the attenuation can significantly change. On the right side, the space to space, the lack of atmosphere actually is advantageous because the total attenuation is lower. So that can actually provide us some advantage. So that's why the stratosphere to space and space to space scenarios for sub-terahertz can be easier starting points than the terrestrial counterparts. Of course, on the terrestrial side, I'm not talking about body area networks. For those, obviously, these bands can be marvelous. So this is where we have been looking into in terms of the usage of these frequencies. I'll start with the first test bed that I was involved with. TÜBİTAK is the National Research Center in Turkey, and there we had sub-terahertz communication setup in the MITEL lab, Millimeter Wave and Terahertz Technologies Research Lab in TÜBİTAK, that's located in Gebze city, Turkey. Here we had the frequency extenders. I will keep talking about these extenders throughout the presentation. They are basically frequency multipliers, and then followed by filters, so that we can generate the target carrier frequency. This is a point-to-point setup. Most of the test beds use horn antennas, and for alignment, we were using a laser source to make sure that they are aligned. So this is a regular measurement picture. So we were sending a pulse train and capturing the peak values. So depending on the let's say transmitter and receiver separation, our measurements basically give two slopes. This is a multi-slope, say large scale fading model. And when we do the data fitting, we can see that there is this piecewise linearity involved in the measurements. And we continue to do different, extend the measurements with different distances between the transmitter and receiver. And of course, some with some tilt, and the amplitudes slightly change. So I'll try to explain why this happens later on. But what is critical is these kind of channels. Of course, the reflection, especially in such a let me go back here. Obviously, we try to eliminate the reflection. So there's no reflection, there's no fading. But where does this randomness come from? Slight randomness. There are different effects. There is the humidity that can affect the measurement, and the temperature that can affect the measurement. So environmental conditions, first of all, are critical to be able to accurately understand the power level. So in the first test bed in TÜBİTAK, we started with using the waveform generator and the scope. Then in 2021, I switched my university from Istanbul Technical University to Polytechnique Montréal, and we started working on in the same not same but similar setup through the use of extenders. So we started with arbitrary waveform generator and the scope. Later on, arbitrary waveform generators, they are, of course, they are very accurate in terms of signal generation. But from the programmability side, we preferred switching to programmable radios. So we started using these USRP B200s. That's very say low-end programmable radio, and through the use of a local oscillator, we are feeding the frequency extender that was moving the carrier frequency 280 gigahertz. So the local oscillator on this side, this box I'm talking about, is here. And at the end, we are basically transmitting this signal, and we capture it with the scope on this side of the picture. So as you can see, there are multiple components in such a signal generation. So we are basically we can do multiple let's say frequency extensions to go even to higher carrier frequencies, and this is where we started questioning the channel models. So this picture on the right side is the same picture. Usually, when we are in most communication, wireless communication research or papers, the noise is almost always, I'll say, it's very highly likely that the noise is on the receiver side. But now in these kind of setups, we are basically generating a signal using a low-end device, B200, and then we generate another signal to mix them to 6 times the frequency, and send it through the transmit antenna to the receiver. So the complexity associated with these with the signal generation, this two-etap signal generation, can introduce a noise-like behavior even before we transmit the signal. And then, of course, there is the channel effect, and after the channel effect, we need to down convert and then do the demodulation. So because of these two-step increasing of the carrier frequency, the synchronization or the phase alignment between scopes is a critical issue. So if there is some sort of little misalignment between them, it is generating almost like a fading, not as unpredictable as the radio fading scenario, but it is still generating a bit of a fluctuation between the transmission and reception. So this is this needs to let's say this needs to be explored further. But what I'm trying to say is there is the impairment on the transmitter end in these kinds of systems that is not that's not well explored. So that means we can start thinking about the signal to noise ratio of the signal on the transmitter, even on the transmitter end. So given this is the fact, with all this randomness, the potential randomness, with Kürşat, we started looking into mixture channel models. Mixture channel model is a combination of different, say, distribution, and especially mixture gamma is advantageous, first of all, because it's relatively easier to calculate the or to estimate the individual components, and it's also very flexible. So instead of using a Gaussian mixture or a log normal mixture, we opted up for for a mixture gamma channel, and we try to this basically gives us a way to analyze any kind of let's say system in terms of the randomness, and it can be structured based on these mixture equations and mixture parameters, and then the final performance can be estimated. So this mixture basically helps us mimic the contour of a histogram effectively, and with potentially with fewer number of components than a log normal distribution. So this, as you can see in the measurements, in most measurements we observed two dominant components, where and it can also be modeled with up to four mixtures. So to be able to find the decomposition parameters, there are different ways. One of them is to use expectation maximization algorithm. Another technique that I like a lot is to use the hierarchical Dirichlet process. This can at a reasonable complexity, it can help us get the a sufficiently accurate representation of the channel. So in short, what I'm trying to say is there is still some sort of randomness in. I understand that the reflections are not there, but the use of multiple oscillators on the transmitter end can create some sort of randomness, especially given the fact that these oscillators can change their behavior with respect to the temperature. So this needs to be carefully considered. The most I think we have the most argument to convince that these kinds of systems are good for intersatellite links. I am aware that optical links are working perfectly, but this can be a good alternative to a bit wider beam scenarios that can be a good compromise between the full like a lower band RFs and optical links. So if we use those, like if we use terahertz sub-THz in satellites, actually potentially we can make very small antenna arrays, and if we can do accurate beamforming between intersatellite links, clearly we can combat the path loss significantly. Now, in these kinds of systems, the accurate sensing is becoming critical, and this accurate sensing is in three different perspectives. One of them is the angle of arrival. The other one is the angle of departure. And potentially, if we do pre-Doppler compensation, the residual Doppler needs to be compensated. And of course, the complexity of beamforming needs to be handled in a satellite, which is a bit, let's say, constrained in terms of the computational complexity. The second option is to use some reflectors. Actually, reflectors are frequently used, not in this kind of a distributed setup, but mostly within the transmitter end. If we can actually use a reflector to between the satellites, that can help us make the propagate the beam further. So we this is not a mission report I'm talking about. It was just a concept study that we did when Kürşat was preparing his PhD thesis, and there we saw that they obviously if we can align them fully, then we can get very good performance. But even a slight misalignment can significantly reduce the performance. So for those we are talking about, of course, in such a scenario, there is all these three satellites are mobile, so we need to this alignment needs to be well designed. And other concerns that we started looking into is basically what else is going on in space. There could be solar scintillations, which is coincidentally modeled by Ricine distributions. Depending on the solar storm, we can have more. We can have the performance can change, so we need to understand this fully. And on top of it, there can be other impacts in space. In addition to the hardware impairments that I started my presentation with a little bit complaint there can be the electron charge density, hidden celestial body brightness. So these there can be all sorts of factors that can change the effective noise in the platform. In this work with Eray and Pablo, along with Professor Elan Baladi, we tried to analyze the potentially how much error performance or data rate could change for reflect arrays depending on the channel conditions. So the relative planetary positions actually need to be taken into account if you want to get very accurate estimates about the target performance. So another very interesting use case I find very interesting is what we presented at last year's ICC. This was easy to carry from our lab, as if you were at ICC, maybe you have seen our demo. So this work is led by Eray. So the first person is Eray, that's me, that's Halit, and this is Louis. So we try to see how we can extend these systems to multi-user scenarios. So in this setup, there are three sub-6 gigahertz users. Each of them is represented by a software-defined radio, B200, and our frequency extender. This is the channel that I was telling at the very starting part. This is captured over the air, and we used our local oscillator to move the frequency up until the 180 gigahertz range. So this structure we refer to this as extend and forward. As you can see in this kind of setup, there are multiple channels already existing. The critical thing that I would like to mention is the frequency extenders. They all need their local oscillators, and they need to be somehow tightly coupled. So if we have full synchronization between them, the first receiver, the sync at the end, can capture all the data. But if they are not tightly synchronized, then it creates all sorts of problems in the reception. So first, I want to start with this by trying to convince you that this system actually works. This is the received signal level from we are sending QPSK signal, and it can be sufficiently well decoded on the destination. So then we look at the synchronized versus unsynchronized cases. Between the frequency extenders, if we have it works perfectly fine when both extenders are synchronized. If they are not synchronized, then as you can see, the constellation shape changes dramatically. So we are actually using a post-processing, digital post-processing to be able to correct this synchronization issue. So we need to be able to track the synchronization, the phase misalignment, and compensate for that to be able to demodulate ideally. So this is basically all intended for space. Maybe I should go back to the demo picture. Our demo, to be very frank, we aim it for stratosphere to satellite setup. However, we can make it work over 20 centimeters distance between the transmitter and receiver in a reliable manner. Of course, with amplifiers, this distance can be extended. So imagining this can be the distance can be extended, then we can actually use this high frequency band through for different applications. One of them is to be able to detect the reflectors. If there is any, ideally there shouldn't be any reflector in free space, so we would have this free space model. However, if there is an object between the in the transmission trajectory, then that can also be that should also be detected to be able to take the necessary precaution. So in this work exam for her master's thesis, we explored if we can use LFM for object detection. This can this works actually, and then on paper at least. However, there is the compromise of low data rate versus high detection accuracy. Then we extended this same scenario by making use of multiple antennas, MIMO OFDM, because OFDM that can actually provide higher data rates. And with the help of tensor decomposition, we aim to detect if there is an reflection. Reflected component in the detection. This works fine, but at a very high complexity that cannot be accommodated in an actual satellite. So currently we are trying to look at techniques to reduce this computational complexity. So keeping an eye on the time, I would like to discuss the extensions of this work. The first one is basically the localization, integrated sensing and radar, or integrated sensing and communication, or joint communication and radar. These are good, options, but we also need a good sensing between or maybe good understanding of the transmitter and receiver positions to be able to help communication. So there is this kind of mutuality between localization and communication. Communication is, of course, through the use of channel state information and the antenna field pattern. We need to improve the localization, and then likewise we need to make sure that the transmitter and receiver is well aligned to be able to improve communication. So this is a measurement result along that is showing the criticality of the alignment. Even a slightest offset between the transmitter and receiver can significantly deteriorate the system performance in these systems. Of course, we are still talking about horn antennas. They are highly directional. So the omnidirectional antenna model is no longer valid for these kind of scenarios. The second critical part that I see, the terahertz literature, of course, the motivation starts with the high data rates promise that comes from the wideband, but very limited works present wideband deployment scenarios. So up until now, all the results that I presented were narrowband signals. So this is a recent work that we have submitted to ITU Kaleidoscope. This Eray and Nesrin, they They have been working on these RFSoC transmitters that can transmit up to 480 megahertz, if I'm not mistaken. So we basically use this wideband signal and upconvert them, extend them through the first extender, and then recover them on the with the second extender. So all the synchronous phase alignment problems, of course, and physical alignment problems are exist in this setup. So combining this wideband with the directional antennas introduces us the problem of beam squint. Basically, beams at different frequencies point to different directions. So if we are using a wide beam, if you want to send a wide beam signal in a multi-carrier setup, so if I go back to this, each of these subcarriers are they have their peaks at a slightly different position. So this beam squint becomes a critical problem, and it is obviously a function of the offset from the center frequency. So the towards the end, this beam squint basically creates a SNR reduction. So Halit has been looking at this problem, and for as an example, I have these plus the depending on where we align the subcarrier. For example, if we align it at the center of the band, then towards the end of the bands, we will see loss in terms of the signal to noise ratio. So this needs to be carefully taken into account when if we actually want to see terahertz transmission in action. So what else do we do? Do we plan after all this? So at ICC, when we were showing our demo of 20, I mean, we can go up to maybe 40 centimeters between the transmitter and receiver. There was one company executive that joked, this would be an excellent solution for Lego people. So they obviously we are aware that we need to extend the distances. So the first thing that we aim to do is to extend this distance. So we got a power amplifier, new filters, LNA, and with those we aim to increase the distance. On the signal generation side, we are switching to four input software-defined radios, again with going with USRP. So the next thing that we aim to explore is this directional line of sight multi-antenna setup, 2x2. Of course, it comes with own this synchronization issues, or the phase between the transmitter and receiver needs to be corrected. So this is one of the extensions that we plan. The second extension that we plan is joint work with Professor Halim Yanık-Ömeroğlu at Carleton University and Burak Kantarcı at University of Ottawa. We aim to extend these systems by using wideband channel emulators that can model the mobility a bit more accurately. So this will help us explore the high mobility conditions in a more realistic manner. So these are the two deployment-wise extension plans that we have. So to conclude, obviously terahertz has a lot of potential, but we cannot use well-accepted models to estimate their performance. So, for example, perfect synchronization is something that we cannot assume anymore in these kinds of systems. So we need to be more careful about these actual functional, the modeling of the functional blocks in these systems. So there is a lot more research questions that needs to be done, not only on the experimental side, but on the modeling side. The high data rate extensions of line of sight directional MIMO without trying to fetch everything to near field is an open issue. Or usage of these with phased arrays supporting mobility, high or extreme Doppler conditions. The beam alignment between the two ends and also extension to multiple users is seems like a valid research directions as far as I can see. This feedback is something that I would like to emphasize a bit more. When the transmitter and receiver are about 100 kilometers away, or maybe 200-300 kilometers away, the feedback delay also needs to be taken into account. And this delay is basically can create a big issue when we deploy this. Also at Polygram we have now Canada is eligible for Horizon Europe Pillar 2 applications and some other programs. So if you have ideas of collaboration, so I'd be happy to hear about them. Two more mini announcements before I conclude. We are starting a new standardization on collaborative orbital data sharing. That's mostly for sustainability of space networks, so that these constellations, regardless of the technology that they use in terms of the communication, they should be able to communicate with one another. So that's basically the main objective, to push for such a collaboration between stakeholders that currently share space. So if you are interested in this, I would be happy to give more information, or you can just check the website. And finally, we have a special section with the submission deadline on June 1st on secure, resilient, and sustainable space networks on IEEE transactions on aerospace and electronic systems, THZ. So if you have a publication to submit, I will be happy to review it. So with that, I would like to thank you for your attention. And if you have any questions, I'll be happy to take them now, or you can always send me an email.